Okay, good morning, ladies and gentlemen. Again, this is Rush Mahaber coming to you again from Wayne State University. We've been talking about the Math 1800 series on exponentials and logarithms currently, so I hope you guys have been following along. The last video was an extremely long one, so what I've decided to do, if I ever have to go that long again, I'm just going to split it into two videos, which I think this one's going to do. I'll probably do like a 15-minute and then another 15-minute. So let me remind you all the things that we've talked about so far, so you guys don't forget. If you guys looked at the last video, I talked about a lot of nonsense. Let me blow this up so you can take a look at it. And I'll try to do a quick overview so you kind of get it. All right, so we talked about the purpose of logarithms, and that's what all this does. Look at the last video. Okay, I can't begin to reiterate, and how to convert them back and forth from logs to exponents, right? Base exponential logarithmic form to exponential form and vice versa. Then we talked about finding the exact value for logarithms, which is so important, and that's just the intuition. Like if you can't do that, then guys, don't even worry about anything else with logarithms, seriously, because if you can't see that 2 to what power is 32, and then you say, okay, that's 5. If you can't do that, then you're pretty much jacked. And then we talked about the 5 big exponential properties, logarithmic properties. I know I keep saying that word exponential. It must be on my mind today. Okay, which is logs undo exponentials, exponentials undo logs, right? If the bases are the same. But if the bases are not the same, which is what happens here, then you run into these laws of logarithms. Okay, and then I went over a plethora of examples of how to evaluate these expressions. These are not equations. You notice there's not one equal sign anywhere. Okay, these are all equality and how to deal with them. So I would encourage you to take a look at the last video because it was really long, and but though we're really going to have to be, we're going to pop back and forth to use these laws of logarithms in a big way today. I'm going to zoom back in so you guys can see it in a big way today. So and this is the basic understanding. So right here, this is all you really need to make out and everything. So this was section 4.3, which I said was graphing logarithms. We didn't even get to a graph yet because we didn't really know how to use it. I keep misjudging how things should be. So let me see if I can get back to where we were. So 4.4 is graphing logs, okay, and domains of logs and log equations, okay. I'm saying these like these are 3 different concepts. They're all the same concept because they're all required. Okay. Now remember, the pretenses behind logarithms is we needed to find the X intercept in an exponential function. Okay. Look at video 4.2 if you're not sure what I'm talking about. Again, all 3 of the chapter 4 videos linked together. You need to watch all of them. All right. So here we go. Let's graph a log. So let's just give you an example here. Okay. And I'm going to use f of x. And let's say I said I wanted you to graph this. This is our happy little log. It'd be your and mine little secret. Blah, blah, blah. You guys remember Bob Ross? That's what you do. You put a little bush in the corner. All right. I feel like I'm showing my age. All right. So here we go. F of x equals log base 2 of x. Okay. And again, how do we graph anything we don't know what it looks like? Okay. Well, we plot points like anything else. So here's my x, y chart. Right? Now, here's the thing, guys. Plot stuff that looks cute. What do I mean cute? Guys, if you plug in 3 here, then you're going to have to say 3 to what power, 2 to what power is 3. That doesn't even make sense, okay? So, I'm going to plug in 2 here. Why? This is a base 2. So, if I plug in 2, 2 to the first power is 2. Or how about 4? 2 to the second power is 4. How about 8? 2 to the third power is 8. How about 1? 2 to the 0 power is 1, guys, right? So when you graph this guy, just by doing this, you see that when you plug in 1, you get 0. You plug in 2, you get 1. You plug in 4, 1, 2, 3, 4, you get 2, right? You plug in 8, 1, 2, 3, 4, 5, 6, 7, 8, you get 3. And then you get some stuff that looks like that, right? But then, if you are a very intuitive people, which I know you guys are if you're watching my video series, because that means that someone told you that I'm a little crazy when it comes to stuff, and I'm very intuitive, that we always have to look at the domain, right? We only use numbers that are bigger than 1. Why is that? Because they were cute and they made me feel warm and fuzzy inside. It only makes common sense to use numbers that are less than 1 because obviously we don't know if it stops here. Does it go on forever or does it stop here? Like, what happens here? Okay, so it only makes sense to plug some stuff in. So what numbers do we plug in that are less than 1? Well, let's see. Okay. Can I plug in 0? Well, better yet, that looks kind of weird. Can I plug in -2? Can I plug in negative numbers? Well, I don't know. Notice I put it all the way down here. Well, let's see. Log base 2, this is scrap paper, guys, equals -2 equals blah, right? Put a box here. So 2 to the box, right? I'm just converting it back into an exponent. So what's the exponent, guys? 2 to what exponent? It's -2. Yeah, you guys see the issue yet? If this is a number like 1, 2, 3, 4, 5, 6, this should be positive and a whole number. If this number was 0, it should be 1. If this number is, say, negative, say -1, -2, -3, what are negative exponents? Fractions, 1/overs, right? It will never, ever, ever be negative. So we can't plug in negative numbers. So that means all of your negative inputs, gone. Can't do anything there. Yeah, that's why you always got to look at the domain of a log, right? And then, well, what about, well, that means we still did leave some numbers out, right? We haven't checked these guys in here. We looked at the negatives. Let's look at the next guy after the negatives, which is 0. Can I plug in 0 since -2 was garbage? Well, let's see. Let's try to plug in 0. Garbage. Let's plug in 0. Can I plug in 0? So 2 to what exponent is 0? I think you realize by the same logic, if this is a whole number, it's going to be a big number, right? If it's the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, it's going to be a big number. If it's 0, it's 1. And if it's negative, it's a fraction. It'll never, ever give you 0. Shoot, if it's a fraction, it's going to be like a square root. You will never get 0. It's always going to be a number that's not 0. So 0 is no bueno either. Garbage. Okay? So that only leaves numbers that are bigger than 0, but in between 0 and 1, that's in question still. So what number do we plug in? Okay, so let's see here. Well, let's play that game. What number do we plug in, Bob? Well, let's see here. How about a half? Why did I say a half? Because I know my exponents, and I can backwards think about things. I know 2 to the -1 is a half. So if I plug in a half, I'm going to get out -1. What about, what do you guys think the next one is? Probably a fourth, right? Plug in a fourth, that's going to give me -2. You see it's getting closer to something, but it can't hit 0. Plug in a 1/8, it's going to equal 3. So you guys can kind of see what's happening here. Your graph, much like an exponential graph, and note I keep talking about exponential graphs when I talk about logarithms, is because they're so closely related. Log graphs, oh, that looks awful. Sorry, guys. My goodness. I told you guys I broke my stylus, so it looks really, really tacky when I start writing. Log graphs always look like this. So for any... Goodness, my stylus is doing terrible today. Let me see if I can hold this properly. For any log graph, so f of x, log of any base, of course it has to be positive. They always look like this. They go through 1. Okay? And it always looks like that. So to just prove to you guys, I want you to check this out. Here is Desmos, my favorite graphing program in the world. So let's see if I can do log. Okay, changing the base on Desmos is a pain in the neck. Base, I don't know what the base is, but there it is. Okay, so this is what it looks like. Now I want you to think about something. You notice that you always use logs and exponentials in the same conversation, but that's because they are the exact same graph. Let's see if I can get you an exponential here. Let's do a. Oh, I can't do a. How about 2? right? You notice I said they all look the same, right? So if you guys are still confused on on what I'm talking about, you need to go back and look at the video 4.1 and 4.2 because those talk about exponential graphs. Remember, what do we use logs and exponentials for? They undo each other. They are inverse functions. They are the reason why the one could not exist without the other one. Let's put it like that. Okay? So how do I do an exponent on here? Oh, I have to do caret. How do you do caret on here? Yeah, I broke my keyboard too. I spilled a whole bunch of coffee all over my keyboard. Isn't that something? Alright, so maybe they have a... Oh, beautiful. Log... raised to x. There's an exponential. Notice the exponential has a horizontal asymptote, while the logarithm looks kind of like the exponential, and there's a vertical asymptote. So they're very closely related, very, very closely related. So guys, I'm going to encourage you to always know the difference. They're so closely related. And I always feel like in life is a microscope. Sometimes you got to zoom out and get the big picture. Sometimes you got to zoom in and get the small picture. When you zoom out and get in the big picture, that's when you're looking at when things have in common. When you zoom in, that's when you're looking at things that looking at the same things, but you're looking at how they're different. Logs and exponentials are part of the same family. That's a zoom out perspective. Now, if you go back in and you look at it and you zoom in, they are very, very, very different. And because they're very, very, very different, you must know how they are different. Asymptotes are a good indicator. Exponentials have horizontal asymptotes. Logarithms have vertical asymptotes. Exponentials go through 0, 1. Logarithms go through, is it going to do it? 1, 0. Okay? Logarithms look like they bottom out, but they really don't. This goes up. It just climbs really, 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 really slow. This guy climbs really, really, really fast. Okay? So these are all similarities that you must have, must know the differences towards. That way you can start using them. All right. Pretty easy, right? Now, we did all this stuff to graph it, but I want you to notice something. What's the domain of this graph? This thing, which is your x's, right? This thing, your x's, which in this case is this piece, must be strictly greater than. Notice it can't be positive. So, this brings us to the next piece of our conversation, right? And graphing logarithms are easy, and we'll talk about it. But before we do that, let's talk about the things you can plug in. Okay? So, actually, no, maybe we should talk about just graphing it. So let's do a quick graph real quick. Let's graph. Before we talk about domain, I want to graph f of x equals log base 2. And it could be whatever base it wants. It could be natural log. It could be, I don't know, you name it, it could be it. So this is what I want you to do. I want you to start with the log that is base 2. And watch what I do here, guys. I want you to start with the log that is base 2. And that's what I want you to do. First, I want you to shift it to the right 1. Excuse me, shift it to the left 1. Then I want you to flip it left, right. Then I want you to flip it up, down. And then I want you to move it up 4 steps. 4 is going to be a big number. How about 1 step? You see what I did there? So this is just another basic graph that you have that you need to do a left, right shift. Flip, flip over to X, flip over to Y, up, down shift. It's a really, really simple graph, but it often can take much, much time. Dang, we're already 13 minutes in. All right, so here we go, 4 graphs, and don't forget you got to find your X and Y intercepts. And this is much like an exponential, so you might need to use an exponential to undo the log. Ta-da! All right. Oh yeah, video 2 is definitely going to have to be different, so I'm going to alter this. This is not going to say log equations. Actually, we'll probably talk about log equations and exponential equations in the same video. All right, so let me do some things here. Let's alter this and say that's just this. Okay, because by the time we get done talking about this in domain, it's going to be pretty much done. All right, so let's do this. So a log graph, here's the basic graph. Vertical asymptote goes through 1, 0. Okay, I know that's really ugly looking. All right, here we go. Left, right shift is next. So I'm going to move everything to the left, including the asymptote. The asymptote's there. So this is here. That means this point that's at 1, 0 should now be at the origin. Is everybody all right so far? Yes, it is tacky looking. Now, let's do a left-right flip. Left-right flip. And I always eat my way from the inside out. So left-right flip means I'm going to be flipping around my y-axis. So here we go. Left-right flip. That means the asymptote that was at here will now be here. This point is at the origin, so at the origin. Hugs, hugs, done. Okay, and then finally, I want to do an up-down flip, which will flip things upside down. All right, so now this part that's trailing, this tail that's going down, should be now going up. And then finally, let's shift up 1. I know this is a very, very close, because you guys have been doing this for a very, very long time. I'm just zooming through it so you guys can kind of get the idea of what's happening. Move it up 1. Now we still have to find our x and y intercepts. Now, obviously, if you're keeping track of this point, you can tell what that one intercept is going to be. It's going to be 1. Okay, but we still need to find the x-intercept. So let's go through and find our x and y-intercepts just to prove to ourselves that we know what's going on. All right, so my y-intercept. So who is 0 in my y-intercept? And everybody should be able to tell me that the x is 0, and I'm looking for the y. So what's the original function? Log base 2. So if f of x is negative log base 2 of negative x plus 1 plus another 1. Okay, you plug in 0. All right, let's see if we can get through it. Plugged in 0, right? So this is negative log base 2 of 1 now plus 1. So 2 to what exponent is 1? And once again, natural intuition reigns supreme. That's 0. Proof that that's 0, 1. Done and done. So this point right here, 0, 1. Now, let's find the x-intercept, which is right here. I don't know what this guy is going to be, and hopefully it works out well. All right, so this is 0. Now we need to figure out what this is. Now note, we need to solve for that x and break into the argument. To do that, we're probably going to need an exponential, or your basic understanding of just how things work. Here we go, here we go. I'm going to first isolate for the log. This is where solving log equations come into play, because that's what this is solving a log equation. Don't forget this negative. Now you see this negative and that negative? Multiply both sides by a negative 1. 1 equals log base 2 of negative x plus 1. Okay, so far so good. Now how do we undo a logarithm? Okay, so there's 2 ways, and I always talk about the intermediate algebra way and the 1800 way. Now, I am a big proprietor to always use the 1800 way, which is base 2, and that is to use this. So recall this. Recall, that's not it. That's not what I'm trying to recall. I'm trying to recall 4-3. This is the 4-4 video. Boom. All right, I know this looks like a big cluster of stuff, but no, recall this guy. That logs undo exponentials. That's why we would use the log to undo an exponential if this is the guy we're trying to kill. Now we're trying to kill the log. To kill the log, we need to exponentiate both sides, meaning make the base whatever that base is, so it undoes it, leaving you just what's in the inside. So, getting back to what we were just talking about, okay, here we go. How do I undo this? Well, there are 2 ways. Now, there are 2 ways. Either A, you just go with the basic definition, the definition of what a log is. The base is 2, the exponent is 1, and it's equal to whatever the argument is. Now, this will work every time. Note there's only 1 log here. Sometimes when there is multiple logs, like how you're going to see in the next video, you're not going to be able to do this, and you're going to have to use some more aggressive methods. Here are the more aggressive methods. The base is 2, so I'm going to base 2 both sides. Much like you do anything with any other equation, this is no different. If you base 2 both sides, whatever you do to one side, you must do to the other. That means this becomes the exponent, and this becomes the exponent. Note they are equal still. Okay, so this is not greater than or equal to, they're equal. All right, so this ends up being what? 2 equals negative x plus 1. This ends up being 2 equals, this undo each other, negative x plus 1. Notice it gets you to the same place eventually. All right? All right? So now it all drops down to the same work. That 2 equals negative x plus 1, so that's minus, excuse me, sorry. 1 equals negative x, so x equals 1. So your x intercept is at 1, 0. So for this graph, this is at 1, 0. And don't forget your vertical asymptote is at x equals 1. It's really not hard at all, okay? It's just for you to understand how it works. Okay, so that's graphing them. So note, let's get back to something here where I was talking about domain. Now, if you notice on your final graph, the original domain says that a log must be greater than 0, right? But we did all these transformations, and we ended up having this big thing. So how the heck did it end up back here? Well, good news. I want you to look at this one more time. So recall your domain restrictions. And these are the two you already had, that denominators, because you can't divide by 0, denominators can't be 0. The second one is even roots. Right? If you had a radicand and the index was even, then the radicand must be greater than or equal to 0. You knew these two. This is the new addition with logarithms that we did when we first plugged in points. And that is, if you have a log, base a, and the arguments b, b must be strictly greater than 0. This is the point. So for our previous example, which f of x equals log base 2 of negative x plus 1, this thing, and this is the green light, negative x plus 1 must be strictly greater than 0. So x, now let's solve all of our inputs for our domain, must be just, guys, less than 1. That means all the x values for less than 1 should have some graph on it. So let's look at our graph from above. It's only stuff that's less than 1. Isn't that cool? So when you have logarithms, the point in fact is this piece, is that now you can officially do any domain of any problem, because now you officially know how logarithms work. So let me give you one and show you how this will manifest. Okay, so let's say if I said, let's make it more complicated because you guys are very, very smart. I know you guys have the ability to get through this. Find the domain. And remember, sometimes you may have to marry guys together. So I'm just going to do one with a logarithm, and then I'll give you one to try, and then we'll talk about it on the next video. Actually, I won't even solve this one, be honest with you. I'll just give it to you, show you how to set it up. You can solve it, and then we'll solve it on the next video. F of x equals log base 3 of 2x plus 7 over 2 minus square root of 6 minus x. I want you to find the domain of this guy, and then here is one for you as well. So we'll do a, and then here's b. B is f of x. Find the domain of this guy, e to the x over log base 4 of x squared minus, oh goodness, I'm trying to do this in my head, which is not good for you guys, 9 minus 2. Does that work out okay? 16, that does work out okay, okay? So find the domain of these two and see where it takes you. Okay, note we have multiple restrictions here, so we'll start the very, very next video with this. We'll call this 4.4 Part A. Alright, guys. So once again, this is Rush Mahabra. We just learned about how to graph logarithms. The big picture is finally coming into play. So once again, if you want to go anywhere you haven't been, you're going to have to do some things you've never done. I will talk to you on the next video. Goodbye.